Alright, hello everyone, and welcome to a mathematical model of motion. Very good use of alliteration there. This is only part 1. There will be a part 2, so don't get too excited just yet. So this is all about graphing motion, and we're graphing motion in only one dimension, because 2 dimensions is a pain in the butt. So you're going to learn to interpret graphs of position versus time for a moving object to determine the velocity of the object. You'll describe in words the information presented in graphs and draw graphs from descriptions of motion. And you will write equations that describe the position of an object moving at constant velocity. But you already know how to do that. So the parts of the graph: the x-axis, the y-axis, and you always have to label your axes too. So all axes must be labeled with appropriate units. So when you're putting labels on there, make sure you have the units. So we're going to talk about position versus time in this video. So this is what a position versus time graph might look like. The x-axis is always time. Position versus time. So this is your y versus your x. That means your y-axis is going to be position. Now notice how the units are on here. Position measured in meters, time measured in seconds. Got to have those units on there too. All right, so the slope of this line will indicate your velocity. This is because when you find velocity, it's rise over run, which I think the next slide talks about. Let's see. Oh, this one. Slope equals rise over run, so your change in y over your change in x. But this has units of meters, because it's the y. Your x-axis is seconds, because it's time. You get meters over seconds. So the units of your slope are meters per second. So that indicates the velocity. So uniform motion is defined as equal displacements occurring during successive equal time periods, sometimes called constant velocity. So you can see, like on this graph, it's a nice straight line. So the velocity is always constant. It's covering the same distance each time. So every second, it's covering 2 meters. Here's 1 second covering 2 meters. The next second, it's also covering 2 meters. So that's what we mean by uniform motion. And there it is. Straight lines on position time graphs mean uniform motion. So given below is the diagram of a ball rolling along a table. Strobe pictures reveal the position of the object at regular intervals of time. In this case, once every 0.1 seconds. So there's the same distance covered in the same amount of time. So all these displacements between these successive time intervals all have the same value. So you're going to get a nice looking graph. Nice straight line. Let's say we wanted to find the slope of this line. So 0.1 seconds, it goes 20 centimeters. So 20 divided by 0.1. Gotta have your units. You get 200 centimeters per second. And that's your velocity. And that's just another slide to show you what I just told you. So the steepness of slope on a position versus time graph. So we know that slope is related to velocity. So therefore, the steeper the slope, the higher the velocity. Makes sense? And the shallower or less steep, the smaller the velocity is. So here's some different position versus time graphs that you might get. So these two on the left here are both for uniform motion. Change my color. Here we go. So both of these guys on the left are for uniform motion. In uniform, we can see because we get a nice straight line. So this has a constant positive velocity. This one, the slope's negative, so it's a constant negative velocity. Now over here, we have accelerated motion. We're going to use a different color for that guy. Accelerated motion. See, it's not a nice straight line. It kind of curves. That means it's speeding up. So the velocity between the first second and the second second is smaller than the velocity between the second and the third, which is smaller than the velocity of the subsequent ones. So this is increasing acceleration. You're speeding up. So, you're sitting at a stoplight, hit the gas. This is what your position versus time graph might look like. Now you're coming to a red light, so you're slowing down, you apply your brakes. This is what your velocity or your position versus time graph might look like. You're covering a bigger distance in between here than you are here, than you are here, than you are here. So your velocity is also decreasing. This is pretty steep, less steep, even less. You're starting to flatten out pretty good. So changing slope means changing velocity. I just told you all this. So decreasing negative slope, you're slowing down more, slowing down more. You can see your position. In this first second, you cover about 8 meters. The second one, you only cover 4 meters, then only 2, and then only 1. So A, this could be you going to school or something. You start at home. Start here, here's home. Home. You start at home, and you go forward slowly. So you get a nice gradual slope for A. B, you're not moving. Your position doesn't change. Whatever this position is right here, you keep it for a certain period of time. Let's say it's 10. You hold at 10 for a certain period of time in between here. Now part C, you turn around, so your velocity starts to be negative. That means you're going the opposite direction you were to start with, so it obviously means you turned around. But you went too far past home, so here you'd be at home again. But you just decided to keep on going. So you went away from home. So here, your velocity is negative. Your position is also negative. Negative position means you went past your starting point in the opposite direction. All right, so let's try to label these guys. So during which interval were you traveling in a positive direction? So here, you started out as your starting position. So we're traveling positively whenever our velocity is positive. So this first section is going to be 2 to 5 seconds. So B goes here. So B for this answer, and that for the end. So B, you're traveling positively, and you're also traveling positively here. So we're gonna, which section is that? It's like 6 to 7? Yeah. So B and D, you're traveling in a positive direction. Traveling in a negative direction, negative velocity. So you're going from this last guy, so 9 to 11. So F, you're traveling in a negative direction. During which interval you're resting in a negative direct location. So here, you're resting in a negative location along this path, because it's negative position, so you're resting negatively. So that would be the very first one, so A. Thank you, warning bell, for interrupting. Continuing on. During which interval you're resting in a positive position, so this will be 7 to 9. So position E. It's a nice flat line and a positive interval. Now, during which 2 intervals did he travel the same speed? This one might be a little trickier. So he's traveling the same speed. Remember, speed is different than velocity, and that velocity is speed with a given direction. So if I'm just talking about speed, I don't care which direction it is. I just want the value, the absolute value of the slope to be the same. So that guy occurs right in here. I find the slope of this line and the slope of this line. They're going to have the same values, except this one's going to be negative. But we're worried about speed. And in physics, negative just means a direction. Doesn't mean negative like you would think in math class. So technically, actually, these two have the same speed. Just one's a positive velocity and one's a negative velocity. That's the difference, because they have the same slope. So during interval D and F. All right, now we're going to do one graphing with acceleration. So you start from rest, south of home. So your velocity right here is 0. You can tell because if we draw a line tangent, it'll be nice and flat. You're slowly going to increase your speed. So you can slowly see your speed increasing. The line gets steeper and steeper and steeper and steeper. Now part B, here'd be home. Home is your 0 position. You pass home and you gradually slow down. You can see that this line gradually evens out. Stops right about there where it's nice and flat again. Remember, the slope of a flat line is 0, which means you have 0 velocity, which means you slow to the stop. Now C, you're going to turn around and you gradually speed back up again. See, it gradually gets steeper and steeper and steeper and steeper. And now a line tangent to this curve will give you a negative velocity, which means you turned around. D, continue heading south, and you gradually slow to a stop near the starting point. So in part D, he slows down gradually, and gradually starts to flatten out, and you're right back to where you started. So your total displacement for this time is what? Say it out loud, because I can hear you, trust me. You ended at the same spot you started. Start, finish. Your total displacement was 0. You started here, came by, home, passed it up, slowed down, turned around again, passed home again, ended up right back where you started. Total displacement is 0. Your total distance traveled is probably a lot more. So I mentioned on the last graph about tangent lines. So if we have an acceleration, position for the time graph that involves acceleration, we have all these curved lines. But we can find the velocity at any point by drawing a line tangent to the curve. Now tangent means it only touches the graph in one place. So on a position for the time graph, the slope is positive, like this guy. Nice positive slope. It means the velocity is positive. The slope is negative. Negative slope. If it's 0, you get a nice flat line parallel to the x-axis. If the line is steep, it's moving fast. If it's gentle, it's moving slow. And if it's flat, it's 0. So increasing it means moving forward. So anytime we're moving forward, we're increasing. You see this is all positive slopes. Any line I draw tangent to this curve up into this point right here will be a nice positive slope. And decreasing means moving backwards in a negative direction. So every time I'm moving, anytime I can draw a tangent line that's going to end up being a negative slope, I'm going to be moving in a negative direction. Concavity is also important on these graphs. Concave up means positive acceleration. So this whole area right here is concave up. And that has positive acceleration, which means it's speeding up, which we can clearly see because if we draw tangent lines along here, they keep getting steeper and steeper and steeper until right here. So that's right in there. Concave down means a negative acceleration. So this is all concave down. Slowing down, slowing down, slowing down. And even though we're speeding up in opposite direction. Not for this guy, for this line over here. So that means negative acceleration. So even though we're moving forward here, but we're slowing down. We're moving backwards here, we're speeding up. Since we're moving backwards, it's a negative acceleration. So this chunk over here, even though we're moving backwards, our velocity is one direction, our acceleration is in the opposite direction. But in this case, our velocity is negative, so it points this way. You can tell it's negative because tangent lines will be negative. And our acceleration is positive over here. And because, just a little hint, every time velocity and acceleration point in opposite directions, it's slowing down. We can see it's slowing down because it gets less steep. So this is about the end. Special points, inflection points. Inflection points means points where it changes concavity. That means there's going to be a change of acceleration. So Points P and R show a change of concavity, which means we change acceleration there. Peaks and valleys are turning points. You go from positive to negatives. So this graph would be positive velocity to a negative velocity. That's shown right there. Time axis intercepts. That means when your position is your position is 0. That means you're at the home. This is your home line. Anytime your graph crosses that line, you're at home. That occurs at P and S. That's it. Thank you for bearing with me on that guy.